Hi everyone, I'm Mohit, and today I'm going to be talking about our work on the existence of seedless condensers exploring the terrain. This is joint work with Eshan Chattopadhyay and Noam Ringach. Let's start with introducing the problem. We see that randomness is extremely important in computation. It is very useful for randomized algorithms, cryptography, distributed computing protocols, machine learning, and much more. Most of these applications require access to high quality randomness. However, in practice, randomness is derived from nature and is often of low quality. This motivates the notion of extractors. Extractors transform a weak random source into a uniform random source. Formally, we say a function is an epsilon extractor for a class of distributions if for every distribution in the class, the output of the extractor on that distribution is epsilon close to the uniform distribution. The notion of distance we are using is the statistical distance or the total variation distance, which also equals half of the L1 distance. This study is known as seedless extractors, and they have been intensely studied. For instance, Shore and Goldrake studied extraction from independent sources. Gabson and Russ studied extraction from affine sources. Trevisan and Vadan studied sources generated by small circuits with applications to circuit lower bounds, and so on. We can ask, what happens if for some class of distributions, extractors provably cannot exist? So recall that extractors guarantee that their output is close to the uniform distribution. One way we can resolve this issue is to relax this guarantee and ask that the output be close to some high entropy distribution. This motivates the notion of condensers. Condensers transform a weak random source into a strong random source that might not necessarily be uniform but has much more concentrated entropy. Formally, we say a function is a k in, k out epsilon condenser for class of distributions with entropy at least k in if for every distribution in the class, the output of the condenser on that distribution is epsilon close to having entropy k out. For condensers, we care about increasing the entropy rate. For example, here, the input entropy rate is k in over n versus the output entropy rate is k out over n. And we care about the output entropy rate being much more than the input entropy rate. We also care about minimizing the entropy gap, which equals m minus k out. We see that condensing is extremely useful. For instance, it allows us to simulate randomness computation using only weak random source. For instance, David Zuckerman showed that we can simulate randomized algorithms with polynomial in the output entropy gap overhead. Similarly, we can do one-shot simulations that arise in randomized protocols, cryptography, interactive proofs, and much more with access to only a weak random source. And most importantly, condensers can exist where extractors provably can't. So let's see what's known about seedless condensers in settings where extractors provably cannot exist. The only previous work we are aware of is a recent work by Doron Moshkowitz, Owen Zuckerman, where they constructed condensers for Shor-Goldrake sources and adversarial Shor-Goldrake sources. Apart from that, we don't have any other work, and so we are interested in finding more seedless condensers for interesting models. So here are various models and our results over them. The first model we consider is of NOBF sources. This stands for non-oblivious bit fixing sources. Here, you are given L bits, out of which G bits are good and the remaining L minus G are bad. The good bits are uniform and the bad bits are arbitrary functions of the good bits. We can ask whether it's possible to extract or condense from these NOBF sources. Kankala and Lineal and Bernard and Lineal showed that you cannot extract from NOBF sources when the number of good bits is at most L minus L over log L. Aita and Lineal showed that you can extract from NOBF sources when the number of good bits is at least L minus L over log squared L. And it is still an open question to bridge this gap and figure out the exact threshold for when extraction is possible and when extraction is not possible. And these sources have motivation in collective coin flipping, leader election, and other problems in distributed computing. And even this is wide open. We ask the question, is it possible to condense from NOBF sources in the regime where extraction is impossible? So when number of good bits is less than L minus L over log L. We show that no non-trivial condensing is possible. So for any constant alpha, if the number of good bits is 1 minus alpha times L, then it's impossible to condense beyond rate 1 minus alpha. So next we consider another model, which is a relaxation of NOBF sources, which we call NOSF sources. So these sources stand for non-oblivious symbol fixing sources. Here you're given L blocks of length n each. And G of the blocks are good, which means uniform, and the remaining L minus G blocks are bad, which are arbitrary functions of the good blocks. Throughout this talk, think of L as a constant and think of N as growing. These sources also very naturally arise in various collective coin flipping problems. So we can ask, what do we know about extracting or condensing from NOSF sources? Burgen, Kahn, Kalai, Katznelson, and Lineal showed that you cannot extract from NOSF sources even with one bad block. So then we ask, is it possible to condense from G out of L NOSF sources? And we show that it is not possible to non-trivially condense from these sources. So if you're given a G out of L NOSF source, you cannot condense beyond rate G over L. So we relax our model even further and study what we call ONOSF sources, which stand for online non-oblivious symbol fixing sources. Here you are given L blocks, out of which G are good, remaining L minus G bad. The good blocks are uniform, but now the bad blocks are functions of good blocks that appear before it. These sources are motivated by blockchain, where you can imagine each new block is created in time space and is either uniform or is truly corrupted. And so if it's corrupted, it's only a function of the blocks that have been constructed so far. Let's see what is known regarding extracting or condensing from ONOSF sources. Agrawal, Obremski, Ribeiro, Snitch, Calci, and Visconti showed that you cannot extract from ONOSF sources when the number of good blocks is even 0.99 L. So we naturally ask, is it possible to condense from G out of L ONOSF sources? We show that you cannot condense these ONOSF sources beyond rate 1 over floor of L over G. So this almost rules out any non-trivial condensing, but there is still some gap. Surprisingly, we show that you can condense G out of L ONOSF sources to rate 1 over floor L over G. We find it highly surprising that this function 1 over floor L over G turns out to be the correct function where condensing is possible and where condensing is not possible. Let's visualize this. So here on the x-axis, we have the input entropy rate G over L. On y-axis, we have output entropy rate 1 over floor of L over G. The red dotted line represents a trivial condenser, which is just the condenser that outputs the input source directly. And on blue line, we have our non-trivial condenser. And you can see that we somehow have many sharp thresholds. For instance, when input entropy rate is 1/3, then no non-trivial condensing is possible. But even if it's slightly more than 1/3, then we can condense to rate 1/2. Similarly, there's a sharp threshold at 1/2. When input entropy rate is 1/2, no non-trivial condensing is possible. But even when it's slightly more than 1/2, then we can condense all the way to rate 1. We record this below. So we say that there's a sharp threshold when the number of good blocks is L over 2. When the number of good blocks is L over 2, it's impossible to condense. And when it's L over 2 plus 1, you can condense to rate 1. For today, we will focus on proving the possibility result. Formally, we will prove when the number of good blocks is greater than L over 2, then there exists a condenser so that for any G out of L O and OSF source, the output of the condenser will be epsilon close to having entropy m minus O of log n, where m is the number of output bits and it equals n, the length of each block. Remember, the length of each block n is huge, it's growing, while the number of blocks L is a constant. To construct these condensers, we will use two-source extractors. Two-source extractors are seedless extractors which take in two independent weak random sources and transforms them into the uniform distribution. Formally, we say a function is a k1, k2 epsilon two-source extractor if for any two independent sources, x1, x2, where x1 is over say n1 bits and has entropy at least k1, while x2 is over n2 bits and has entropy at least k2, it holds that the output of the two-source extractor on x1, x2 is epsilon close to the uniform distribution. We will in fact need a strengthening of two-source extractors, which we call output light two-source extractors. We say a two-source extractor is R output light if for all Z in the image, that is for all m-bit strings Z, the size of pre-image of Z under 2x is bounded by R. Or in other words, the number of xy such that 2x of xy equals Z is at most R. We will use amazing output like two-source extractors to construct our condenser. In particular, we will show that there exist R output like two-source extractors where the length of the second source will be very small. It will be logarithmic in the length of the first source, and the number of output bits will be linear in the length of the first source. So the length will be O of n1. And moreover, the output lightness parameter R will be O of 2 to the n1 plus n2 minus m, which is near optimal. And in fact, we can show that a random function attains these parameters, and we will use it. So with this, we construct our condenser. So remember, our constructor takes in L blocks x1, x2, xl of length n each. For blocks g plus 1 to L, we will take a small prefix of length roughly O of log n. We will let the length of the prefixes be geometrically decreasing with the next block. So for the ith block, we will take a prefix of length 20 to the L minus I plus 1 times log n. We will then concatenate the first G blocks together, and we will concatenate these prefixes of the last L minus G blocks together and call these strings Z1 and Z2. We will then output 2x of Z1 and Z2. Visually, this is what's happening. You have your first G blocks, which you concatenate, call it Z1. You have your last L minus G blocks, for which you took small prefixes in a geometrically decreasing fashion. You concatenate these prefixes and form Z2 and pass both these strings to the two source extractor. And its output is the condenser's output. So let's show that our condenser is indeed correct, i.e., for all O and OSF sources with G good blocks, the output of the condenser has very high entropy. So first we consider those O and OSF sources where the last L minus G blocks, all of them are bad. For these type of sources, it must be that the first G blocks are all good. This implies that the string Z1 will be truly uniform, while the string Z2 will be arbitrarily corrupted, and Z2 can in fact even depend on Z1. Here we will rely on our output lightness property to show that our condenser works. So by way of contradiction, assume that the output of the two source extractor is not close to being condensed. Not being condensed is equivalent to saying that there exists a small set, capital D, with probability that the two source extractor outputs an element in capital D being at least epsilon. In particular, this implies that the size of the pre-image of D will be very large. And because we carefully set the parameters, we can conclude that, and by an averaging argument, we can conclude that there exists an element in D which has very large pre-image size, and in fact it will be so large that it will contradict our output lightness property. And hence this will allow us to conclude that our condenser in this particular case will in fact output a source with very high entropy. So now let's consider the other case where there is some block J greater than G such that Xj is uniform. In this case, because G is still greater than L over 2, there must be some block amongst the first G blocks that is uniform. This implies the entropy of Z1 will at least be linear in its length. Next, we will consider fixing the output of blocks YG plus 1 to YJ minus 1. Condition on these fixings, Z1 will lose some entropy. The amount by chain rule, the amount of entropy it will lose will be sum of the lengths of these blocks. But because Z1 is so big and because it has almost linear entropy, and because the yi's are of such small length, the amount of entropy it will lose is very small, and it will still have lots of entropy, enough for the two source extractor. Also importantly, because X is an online NOSF source, the block Yj will still remain uniform, conditioning on fixing the blocks Yg plus 1 to Yj minus 1. Okay, now if the blocks Yj plus 1 to Yl were all uniform, then we'll be in great shape because then the blocks Z1 and Z2 will be independent sources with relatively high entropy, and by the property of our two source extractor, the output of our condenser will be uniform. However, it could also be that all of these last L minus J blocks could be bad, and the adversary could control them and make them depend on all the blocks before it and make Z1 and Z2 lose independence that is crucial for the two source extractor. However, we can show that the adversary cannot make things too bad. In particular, we will rely on the following lemma. Let D be a distribution such that the two-source extractor on D, the output is epsilon close to being uniform. Let D prime be a tampered distribution which looks just like D, except adversary controls some B bits. Then the we can still guarantee that the two-source extractor on distribution D prime will output a distribution which has high entropy, which is entropy at least m minus b, and the error will be increased by a factor of 2 to the b. And using this crucial lemma, we will save our proof. In particular, we will let D be the distribution where we have Z1, Z2 both independent, and Z2 has high enough entropy, and let D prime be the distribution where the blocks yj plus 1 to yl are all controlled by an adversary. So, as the blocks yj plus 1 to yl are all controlled by the adversary, the number of bad bits b is the sum of the lengths of these yi's. By the above lemma, we can guarantee that the output entropy will be at least m minus b. Also, because m is proportional to the length of z1, which is very large compared to the length of z2, we will still have lots of entropy. More importantly, because we choose the length of these prefixes in a geometrically decreasing fashion, we can guarantee that the length of the block yj will be at least 10 times the sum of the lengths of the remaining blocks after it. In particular, it will be at least 10 times b. This crucially helps us bound the error of our condenser. So the error of a condenser will be at most the error of our extractor times 2 to the b, which is at most 2 to the minus length of yj over 4 times 2 to the b. And because length of yj is so big, this error will still be pretty small. And so we can conclude that our output, even in this case, will have high entropy. And this concludes our proof of our possibility result that we can condense O and OSF sources to rate 1 when the number of good blocks is at least L over 2 plus 1. We finally end with some interesting open questions. First, can we find explicit condensers for O and OSF sources? The condenser construction here required amazing two-source extractors that are output light. And we could only show their existence, and we were not able to explicitly construct them. Second, can we construct condensers for other parameter settings, for instance, when n is constant and L is increasing? This parameter setting is strictly harder than our current parameter setting, where n is increasing and L is constant, and so it will be interesting to extend our techniques to such regimes. A special case of this question is when n is a constant. So you're given L bits, out of which G bits are good, L minus G bits are bad, and the bad bits depend on the good bits that appear before it. We call these online NOBF sources or ONOBF sources. And we ask, is it possible to construct condensers for them, or can you rule out condensers for these sources? This concludes the talk, and thank you very much for listening.